Uh, Hello, can you please confirm if I'm audible?
We can hear you, sir.
Okay, fine. Yeah. So that's great. So maybe some people can join later. So we can start with the live session for the week 7 for the course Introduction to Semiconductor Devices, which is taught by Professor Naresh Kumar Imani from IIT Hyderabad. And I'm Anant Singhal, a PhD student from IIT Jodhpur. And I'll be assisting in solving some of the similar week 7 assignment problems that will help you in solving the assignment that has been given to you for the corresponding week 7. And if I go to the course content, so like we have already covered half of the course. So as I told you, I guess in the previous class also we had a certain flow, like we went from a single bar of a silicon, we doped it. Initially it was intrinsic, then we doped it. Then we had some different doping contacts. Then we got to the PN junction, and in the last lecture we discussed about some of the metal semiconductor junctions, that is when we take metal and a semiconductor in the contact. So this is already covered. So if you have a good idea about how these things are happening, how the band bending is happening, and how the electrons or how the holes are getting transferred from either of the junction, then you'll be easily able to grasp all the concepts in the further classes. So most of the classes from now will be covering the major topic for your course or for your career also, that is the MOS transistor, which is the metal oxide semiconductor field effect transistor. And we'll start with the MOS capacitor first, because ultimately this MOS capacitor is basically the heart of the MOS transistor. So as we'll go one by one again, so we'll be studying MOS capacitor first, and we'll make the MOS capacitor a MOS transistor in the next class, or from maybe from next to next class, whenever we came into the course, whenever the topic comes in the further weeks. And in this week, we'll be basically dealing with how the MOS capacitor works, and why is it better, or why it gives the characteristics that it should or it is giving. And then we'll also talk about the same thing, like the potential diagrams, that is the band diagrams in electric field for a MOS capacitor, that will be similar to that we have from PN junctions and different things, because again MOS is again metal oxide semiconductor. So we'll have the contact of three different types of materials. One is a metal, one is an insulator, which is oxide, and last is a semiconductor, which is just semiconductor. And then we'll also be talking about what is this accumulation region, what is the inversion region, what is a gate voltage drop across a MOS device. So we'll be covering each of these topics in this particular lecture. So yeah, before starting or before going into the MOS capacitor, yesterday we discussed some of the topics, or at last we were stuck to the spin diode, and I asked the students to maybe mail me some of the solutions that you can solve using your understanding of the course. So I've got, I guess, two solution. One is I'm not sure if you have joined the class. One is, I guess. Um, One student sent me a document. So is he here? I'm not sure who sent it.
Yes, sir.
Okay, yeah.
I see.
So yeah, okay, okay. So like this is more or less correct. So we can have two different explanations. I guess there is one more student who sent me a diagram which was looking like this. Is he also here, or is she also here? I'm not sure. Um, did anyone else send me? Except, can you please tell me your name? Is it Ramaya, or hello? I hope I'm audible. Can you guys hear me? Please let me know.
Yes, sir, we can hear you.
Yeah, so what is your name? Can you please tell?
Myself, Ramaya.
Ramaya. Okay, fine.
Yes.
And I guess someone else also sent me a solution which was looking like this. Is he or she is in this meeting? Yeah, I hope, I guess not. So, okay. So I'll let you know, like both of these solutions are correct, but from what perspective we need to look at, I'll let you know, and we'll maybe make some more band diagrams that will be, I guess, very interesting for all of you to do. So if I talk about a pin diode, so pin diode, as I said in the previous or in yesterday's classes, it is nothing but a P and some intrinsic region. So intrinsic means that EF should be at EI, or the Fermi, there is a 50% chance inside at between the electrons to have uh, the electrons to be get occupied. So we know that for a p type, if I draw, let's say we are doing it in equilibrium. So for p side, we know that what we have this ei, and where is the ef? It should be near to the valence band. Now this we already know. For intrinsic, if I say, so this is ei as well as ef, because we have an intrinsic semiconductor. So here n is equals to ni. If I go through the complete formula, it is, if you remember, it is EF minus EI over KT. And the EF and EI coincide for the intrinsic semiconductor. So basically N is equals to Ni is equals to P. And for N type of semiconductor, we know that we have a EI and we have this EF, and this is EC, this is EV. Yeah. So now if we can see that the highest Fermi level that we have is here. So the electron will flow from the higher Fermi level to a lower Fermi level, and same goes to the here. So basically what we can say is, since this is the going down the most, so the band will be bending upwards for this by some bit. Similarly, this is also going upwards, so it will also bend by some bit, and ultimately we will have this at the most higher end. So maybe I can make it, that will make, yeah, maybe I can make it by myself, that will make it more clear. So what I'm saying is, since this is going down, so maybe I'll make the EF is here, EV is here, and EI is here. And since now what I have done is I have considered a considerable length of this particular intrinsic region. So this is the main point of the pin diode. So what we do is we take a very large length of intrinsic semiconductor in between a P and a N junction. So why do we take it? Because like in the application criteria, like if I talk about the real world problem, so what we want is we want a device to work very fast, right? So for very fast, we should have lower capacitance. I hope you are able to get this lower capacitance because, sorry, so more the capacitance, more will be the delay in the circuit. So basically we know that the time constant is given by RC. So if we have a higher capacitance, we will have a slower device. So what we want is we want a lower capacitance, and capacitance we know, sorry, is nothing but epsilon A by the depletion width. So basically capacitance is inversely proportional to the depletion width. So if I have a higher depletion width, I have a lower capacitance, and if I have a lower capacitance, that means my device is working very fast. So this is the main application of pin diode, which is, I guess, will be taught in the further lecture. So I guess optical, there is some lecture on that. Yeah, so optoelectronics will cover this pin photodetector. You can see there is a topic in the further classes. So that will be nothing but P plus I N plus pin photodetector, and I'll let you know how it is working. So basically the working will be same that I am explaining now. So to make the device faster, that is what we are doing. We are increasing the depletion width. So this intrinsic region will have some N as Ni, and for this P plus we will have a very high doping. So the depletion width grows into this like this, and same is the case for N plus and I. So we will have a very high effective depletion width, and that makes our device faster. Yes, it takes more area and more power, but what we want ultimately is to make our device very fast. So this is why we generally use this pin diode. So since now I have taken a very considerable length, so what I can do is I can make this maybe something like this. So band will surely bend near the depletion region, and it will get again saturated for the EI. Sorry for the bad drawing. So again, the Fermi level is here only. Yeah. So let me make a complete line of Fermi level. That will make it easier. So this is the I region. This is the N region. And if I now draw the P region, so we know that it is near the Fermi level now. The conduction band should be near. So it should bend like this, and again, like from here it will start to grow the EI level, and we have this. So this is EC at P, this is EV, this is EF, and this is now EI. So I hope you are able to get this, what I'm trying to say here. So now, if I talk from the perspective of a very thin I as compared to a very thick P. So let's say this is P plus again. So all the depletion widths will be here. So in the depletion region, what we'll consider, or what we will have a change in the electric field, because we have a depletion width, so we will have a considerable change. So if I make the band diagram for this corresponding upper diagram, maybe I should not have made it here. Let me be very clear. So this is P, this is I, let's say this is N. And if I take now the case, maybe I can make it here. If I now take the case when I have some P, some thinner I as compared to the previous case, and some higher, thicker N. So what will happen, because we have the depletion width for P plus, we will have a smaller region and we will have a higher here. Again for N, we will have a higher. So in the depletion width, what will happen? We will have a certain change in the electric field. So there will be some band bending. So if I take a very thinner intrinsic semiconductor, so the diagram will not get what to say, constant. The EC and EV level will not get constant for some time, because for the whole intrinsic region we are experiencing the electric field, or the whole intrinsic region is carrying the depleted carriers. That is, for this case it will be Na minus, and this will be Na plus. So this will look similar to a diode if this is very thinner as compared to the previous case. So are you able to get the same what I'm trying to say? So we will have a complete difference in the intrinsic. Yes, for sure. What will happen is we will have a higher built-in potential because of this some wider region. But ultimately, what we have is, so this is the built-in potential. The total built-in potential will be this for this particular case. So we do have an increase because of this intrinsic region in the built-in potential. But the characteristics will look similar to the PN junction if I take a very lower width of this intrinsic junction. So does it make sense to everyone? Both the answers will be correct. So one of the students sent me this, and one of the students sent me this. So both will be correct. So here what we have is, we have the Fermi near to the valence band for the P case. Here we have the Fermi near to the conduction band for N case, and here we have the Fermi level in between the conduction and valence band for the intrinsic case. So it does make sense. Again, it makes sense for this answer also, in which what we have is, we have the change in the EC and EV for the whole barrier, because we have a thinner intrinsic layer as compared to the P type and N type. Uh, so is it fine? Any doubts in this?
So for the entire depletion region to belong to the intrinsic region,
Yeah.
either we could increase the doping of P and N side, or we could reduce the width of the intrinsic region, right? Either way
Yes.
it works.
Yes. Yes. So in
Okay.
general, so as I said, like application wise in the real world, we have this spin photodetectors, in which what we do increase the doping of this P and N. We do not like decrease the width of the intrinsic region. We do make them equal, but we do have increase in the dopings to make this happen. So this will basically, because we ultimately want to have a higher depletion width, right? So that will be a have some bad effect on the device, because ultimately we want a device to make or to run fast. So this is not a good way to go ahead, but instead of that we should increase the doping to have a good effect on the device.
Okay, sir.
Yeah. So now, maybe out of curiosity, what all of you can do is, if possible now only, maybe we can take three cases quickly. So maybe you can try to make now only at equilibrium again. That will be very good if you are able to do this exercise right now. Sorry. So you need to make again the band diagram. Maybe we'll only take two cases. One is will be a simpler one. So a PNP junction, and the next will be P plus P, N, N plus maybe P. Let's take five different dopings. So let's say the P junction is having a doping Na of 10 raised to 16 per centimeter cube. The N is again Nd, which is 10 raised to 16 per centimeter cube. N plus is, let's say, 10 raised to 18 per centimeter cube. And sorry, P plus is 10 raised to 18 per centimeter cube. So are you up for it? Do you want to do it right now? It will be good if you want to do it. Please let me know, otherwise we can move forward.
We'll do it, sir.
Okay, fine, yeah. So that would be great. Maybe do it and share it with me with using something. Maybe you can mail me or something like that. So you can take maybe 2-3 minutes to do that, and then we'll move forward. At least for the first case, you can take 2-3 minutes because this will be very easy to do. So PNP is, I mean PNP, by PNP I mean something like this. This is P dope, this is N, this is, sorry, this is P. Yeah. So yeah, so let's wait for 2-3 minutes, and then I'll also solve it. Has anyone tried the first case?
Yes, sir.
Okay, is there some way you can show it, or
I will mail it to you.
so you're mailing it right now?
Yes, sir.
Okay, sure, sure. Do that. Okay. So yeah, maybe you are still mailing. Uh, so let's do the solution now. So we see that we have a higher Fermi level for the N type of doped semiconductor, while we have a lower Fermi level for the P type of doped semiconductors. So yeah, I've got your solution. So yeah, that is correct. So basically what we will have the electron flow from higher Fermi level to a lower Fermi level. So what it will do, it will have the bending upwards, because this will go basically down for both the cases. And what I'll get is, let's say I have this as a Fermi level now, and this will be what? This will be P, this will be P, and the Fermi level, sorry, this will be EC, EV, this will be EF. Yes, okay, sorry for the bad drawing. This would be much flatter here. So this is basically where we have some change in the electric field. So you can see the Fermi level has aligned. So at the N region, it is closer to the conduction band, and for the P region, it is closer to the valence band. And we have a band bending like this. So for a p-n junction, if I say, if you just see this, only this region, maybe I can highlight. So if you see just this region, so this is what we draw for a p-n junction. So now what we have done is we have made two different p-n junctions. So one we have the other side. So what we can clearly see is we have two p-n junction which are just getting adjoined. So this is what we get. So this is the correct answer. So the one answer that you have sent me is also correct. So we can now quickly do it for the second case that I have made. So that will make your understanding very clear. So we have P plus P, N, N plus P. So we have P plus P. Let me make it a bit wider, because I hope you are all doing the same. And if you have already done, you can mail me again. So let's say we have no junction. Yeah. So if I make a very small schematic for all the band diagrams without the contact, so we have this EI. So we have the EF here very close to the valence band because of the higher doping of P plus. Then we have the EF here for P region. The same will be here.
So EF should be closer to EV, right?
Oh yeah, yeah. Oh yeah. Sorry, sorry. So for P plus, the EF will be very close to the valence band. For P, it will be close to the valence band, but not as it is for P plus, and same goes here. And for N, what we have is we have the Fermi level close to the conduction band, and here very close to the conduction band as compared to the other case. Yeah. So what we'll have is we have the highest electron concentration flow here, like the highest Fermi level here. So electron will flow like this only. So if I try to make like very quickly, so what we have is we have a single Fermi level. So as you can see that N will be lower. So what I can do is, okay, I'll start with P plus. Where is P plus? So yeah, here is P plus. So this is, let me not make a very long line. Yeah, Fermi level will be the like this only. Now we have a P. So higher level will be this. So band will bend a bit upwards. We have this like a very small. I've made it very larger, I guess. I hope it makes sense to everyone. So this is P. Now we have a N. N is what? N is the conduction band now. So again, let me small. So what we have is we have this. So I'm making the dotted lines that will make it more clearer. Yeah. So now what we have is we again have a N plus. So it will go a bit lower again. And then we have finally the P. So P will should align to this P. So yeah, this will be it. So let me write again the different regions. So this is P plus, this is P, this is N, this is N plus, this is P, and this is EC, EV, and this is EI, and this straight line is a Fermi level. So does it make sense to everybody? Is there any
Yes, sir.
doubt in this? Anyone else? Is there any doubt? Okay, so I hope now you are able
No,
to,
sir.
yeah. So now I hope you are all able to make these band diagrams and you are able to understand the flow of electrons and holes through these junctions. So now without any further wait, let's start with the uh, course content for this week that we have for MOS capacitor. So we'll be starting with the MOS capacitor. Like I'll let you know the very basics. Uh, in fact, what is MOS capacitor and why are we even using it? So I hope you already know what is a capacitor. So can anyone tell, like structure wise, how do we have a capacitor? Like if I talk about a parallel plate capacitor, so what is a parallel plate capacitor? Can anyone tell?
Helps us store charge.
So that is a function of capacitor, that it stores charge. So if I try to make a parallel plate capacitor, so what we have is, we have a metal plate, we have another metal plate, and we have some dielectric in between the capacitor, having some depletion with D. Let's say, sorry, let's say I'm not applying any voltage as of now. So what we have, some depletion with D, we have some cross sectional area. If I try to make maybe some 3D, so we have some cross sectional area which is A, and we have some depletion width, and we know that capacitor is nothing but epsilon A by D, where this epsilon is the permittivity of this particular dielectric. So I hope this is a very basic of capacitor. So what we have, a metal, oxide, and a metal. Does it make sense to everyone? Like, this is a very basic capacitor. Is it clear?
Yes, sir.
Yeah. So what I'll do now, so let's say I have a metal, let's say I again have a oxide. So let's say I'm writing this as metal, I'm writing this as oxide. So what I'm doing now, I'm putting a additional dielectric, which is what I'm naming as substrate, or you can say this is a semiconductor material, and at last I'm again having a metal. So for the above case, we know that this will be constant, is irrespective of anything. So if I try to plot the capacitance with reference to the required voltage or applied voltage, so what we'll get is, we always get a constant capacitance, because it is dependent upon the geometry of the device, that is epsilon, which is the dielectric material property. Again, area is a cross sectional area, and D is the depletion width, or the width between the distance between the two parallel plates. So what happens if we apply this additional substrate in this between of the capacitor? So what we see is, maybe I can plot in that same plot only, that will make more sense. So what we see is, we have a certain equivalent capacitance for some region, but in between what happens is, the capacitance decreases and it again rises up again. So this purple one is belonging to this particular what to say, structure. So this is what we have, or what do we call as MOS capacitor. So MOS capacitor is nothing but metal oxide semiconductor. So we have metal, we have oxide, we have semiconductor. So this is just a contact layer. We can ignore this. So this is why we are, first of all, why are we calling it a capacitor? Because again, it will store charge, but in some another way. So we have some variable capacitance associated with a MOS capacitor. So that is why we also call it as a variable capacitor. So now if I draw it like rotating it maybe 90-degree clockwise. So what we have is, we have a metal. Let's say we have applied some voltage. I have a metal. I have some oxide. Let's say I'm naming it as SiO2, and I have some substrate. Let's say this is semiconductor, and again a very like small metal, or a thinner metal, and ground. So this is what is MOS capacitor. So is there any doubt in this? Any doubt? Anyone? So the heart of the MOSFET basically is the MOS capacitor. So if you are able to understand how this MOS capacitor is working, you will be able to understand anything. And what we'll majorly look at, so again, so we had, sorry. So we'll have the main interest at the semiconductor. So this is the semiconductor and this is the oxide. So we'll be mainly looking at this semiconductor and SiO2 interface. All the interesting thing will happen here. Like all the charge and all after applying voltage will be getting affecting this particular interface. Silicon and SiO2 interface. So the metal can be anything, maybe you can take aluminum or any metal, but most of the cases, like in the application wise, what we take is we take a what we take is a polycrystalline silicon that basically acts like a metal. So I'm talking in terms of application wise, like in the actual devices what we have. And then we have this silicon substrate, we have the oxide as SiO2, and at last we again have a polysilicon to have the what to say, to have the contact at the bottom. So again, if I try to make the band diagram, like a very basic band diagram, so what I can do is I can take a metal, so this is oxide, this is metal, and let's say this is semiconductor. Okay, so let's say I'm taking maybe a p type substrate as of now, and again there is no applied voltage. So what we have for the p type substrate, we know that for the p type substrate we have the Fermi level here. And metal, what we know is we have a very high number of what to say, electrons. So I'm making just the EF for metal will be very high. And for oxide, we know it is an insulator, so it will not, so this is an infinite line. It will not let anything pass through this. So let's say this is vacuum. So this is what we have if I don't make anything. So this is what we call as the flat band condition, when there is no band bending at the contact at the interfaces. Does it make sense to everyone? I hope this is not getting confusing. Or so this is again Q5M, which is a work function as we discussed yesterday. This is the electron affinity. Again, so if I make maybe, sorry, yeah, so sorry for the glitch.
Condition.
Uh, Sorry, am I audible? I hope.
Yes,
Hello.
sir.
So I guess
Please,
I,
yes, sir.
okay, sorry.
Please, repeat again
Yeah, yeah,
on flat bending condition.
yeah, sure, sure. So I hope, I guess I lost my network connection. So I'll repeat again. So what we have is, so what I'm trying to say is for the example I have taken, am I audible, guys?
Yes, sir.
Okay, yeah,
Audible, sir.
yeah, yeah. So for the time being, what I have done is I have taken a P substrate, semiconductor. So that is why I made this, sorry, so it will be here. So I made this Fermi level close to the valence band, which we what we call is the work function of the semiconductor. And we know that the metal will have a very high Fermi level because it is full of electrons only. So I made the Fermi level of the metal very high as compared to the semiconductor side. And this is just the metal and the semiconductor, and in between we have the oxide. So this is just the representation when there is no band bending. So if now what we'll do, we'll apply certain voltages at the metal end. So we'll see some different cases. So what I was saying is this is the particular condition when we have the flat band condition. So like there is no band bending as of now in this particular diagram. Uh, so that is what I've just said. Does it make sense, or is there
Okay,
any?
sir. Clear.
Yeah. So I'll explain the flat band voltage first. What is flat band voltage? So we can clearly see the flat band voltage is nothing but phi ms. Phi ms is the difference between the metal and the semiconductor work function is a flat band voltage. So basically, if I try to denote, so the difference, this particular difference is the flat band voltage. So we require certain flat band voltage to have the flat band. So maybe I can make it, yeah, let me try to make it. Or first of all, let's define the flat band voltage. So flat band voltage is the voltage or it is applied. Yeah, one thing I forgot to add. So for this particular thing, we call this particular terminal as a gate terminal. So whatever voltage that we'll now write will be called as the gate voltage. This thing I want to add. So we have a certain gate voltage that will apply at the metal side. This is the body side. Yeah, so these are the two terminals as of now for the further analysis, and the body will always be grounded for in the initial analysis. We'll talk about the body bias later in the further advanced classes, but for now the body will always be grounded, and we have the gate, which is this particular thing. So we'll be playing with the gate voltage, like we'll be applying certain voltages and see the effect on this particular structure. So what I can say is the, yeah, so flat band voltage is the nothing but the applied, sorry, the applied gate voltage. Again, I'm denoting it with VG. So it is defined as applied gate voltage such that there is no band bending in the in any region, in fact. So what I'm trying to say is, yeah, so maybe again, if I can make, sorry, I'm just ignoring this. Let's say this is metal. So this is VG, this is semiconductor. Sorry, why it is happening? So let's say we have some charges trapped in the oxide. So what we have is, due to some defects, we do have some charges trapped in the oxide. So this is the oxide block, this is the metal block, and this is the gate voltage that I have applied. And again, I'm taking for the whole understanding a p-type semiconductor substrate. Yeah, semiconductor it is, and this is ground. So what I'm saying is, we have some certain charges, positive charges, which are trapped in the oxide layer. So if I try to make the charge density plots, so let's say this is metal, this is oxide or insulator I can write, and this is the semiconductor. Sorry. So as of now, what we have is, we don't have, we have all the negative charges. Maybe I can make it below. Come on. Yeah. So I can make it below. So since we know that we have read in the metal semiconductor junctions yesterday that there is no space charge, like there is a negligible space charge for the metal as compared to the semiconductor. So I'm making this as, let's say this is qm, which is negative because of a lot of holes, and let's say we have some trapped charges at the insulator which are positive, which I'm denoting as qs. Does it make sense to everyone? I hope there is no doubt in this. Please let me know, otherwise I'll explain again.
So could you please explain again how the sign of QM and QS was determined?
How the
Negative and
sign?
positive.
Yeah, yeah, okay, okay, fine. So for metal, I mean, yesterday we had this, sorry, we had this metal semiconductor junction, if you remember. And what we do is, we did take a lot of cases in which phi m was greater than phi s and all. And what we got to know is, when we have this Schottky contact, we have a, in fact, we don't have any depletion width in the metal side, but we have a very larger depletion width in the semiconductor side. And if I take, let's say, q and d, and I was taking this as delta yesterday. So this is what I'm saying, that the metals will have a very smaller depletion width as compared to this semiconductor. So I'm not drawn for semiconductor now, but we have an insulator in between, in which I have specifically added some charge traps at the interface, which are positive. So that is why I'm taking some charges at the interface which are positive. I'm denoting at QS, and this QM is a very thinner QM which is present at the metal side. Does it make sense?
Yes, sir.
Yeah.
Sir, was QS added through the application of VG?
Once what?
How was QS added? Was it added through the application of VG?
No, no, okay. Yeah, so like in general, what happens? Okay, so that is a good question. So what happens is, when we like, have you ever heard about this term fabrication? Like fabrication of devices?
Yes, sir.
Yeah, so during fabrication, what happens is, so we have this p-type substrate, and we generally do the deposition of this SiO2 over this via different methods such as thermal deposition or something like that. So there are some of the majority carriers of holes during the deposition that gets trapped inside this. So these are the non-ideal effects that can happen. So that is what I'm saying. Like ideally there should be no charge, so I should make not make this even a single charge, but in the ideal cases what we have some trapped charges at the silicon interface, silicon and the semiconductor interface, silicon and the oxide interface, sorry.
Okay, sir. Got it.
Yeah, so by application
Sir,
of this yes, yes,
uh, how how it comes, sir? How positive charge comes?
that is what I said. Okay, so let's say we have a, have you ever seen a wafer? So let's say we have a wafer which is p-type doped. So we have everywhere a very high Na concentration, or the positive holes and holes are there. So what happens during deposition, like on top of it, if I try to deposit some of the oxide using the thermal deposition, so these holes or these Nas get come in the contact, and some of the holes get trapped in this particular oxide region. That is what I'm saying. If it is getting confusing, you can just leave this. There is no mean, but ideally I'm trying to explain that in an ideal transistor what happens in general. Does it make sense, or should I leave this? I can leave
Okay,
this. This
sir.
is fine.
I understand.
Yeah,
Understand.
yeah. I guess sorry, what happened? Again, I need to rotate this. Yeah. So maybe can just leave this thing. What I can do is, let's say we have this semiconductor, uh, this VG. This is, let's say, P-type substrate, and this is ground. So let's now play with the gate voltage. So application of gate voltage. So the first case that we'll take, I'm writing this as case 1, that we'll take is Vg is less than VFB, or let's say we are taking Vg as negative. Yeah, so that will be quite good. So what I am doing is I am applying a negative voltage at the gate. Let's say this is some negative voltage. So can anyone tell what could happen if I apply a negative voltage? I'm asking for the interface. What could happen if I apply a negative voltage at the interface?
Majority holes would be attracted towards the
Yeah,
interface.
exactly. So yeah, so that is a very good answer. So once I apply a negative voltage, we know that we have a p-type substrate, right? So what will happen? These majority holes will get attracted towards this semiconductor and silicon surface, and there will be a lot of holes accumulated. So I'm denoting the plus. Plus means the holes will get accumulated near the semiconductor and the SiO2 surface. So that is why we call this region as the accumulation region, because we have accumulation of holes. So let me try to make it via band diagram. So let's say we have this. Yeah, so let's say this is oxide again. This is metal, and we have applied a negative bias, and let's say this is semiconductor. So what we have is we have a holes accumulated once I apply a negative bias. So if I can just leave this oxide part. So what will happen? Uh, we had some negative bias which is attracting these holes, and due to which what is happening? We have the band bending upwards, because we have a higher Fermi level here and a lower Fermi level here. So it will go down. That means it will bend upwards. So maybe I can make this again very high EFM. That is not a problem. And we have a band bending like this. And this will be EFB. Let's say this is EF. So what is happening? We have more holes at the interface. So what I am trying to say is this Fermi level at the interface you can see is moving closer to the valence band. So we have a higher value of Na here as compared to the bulk. Does it make sense to everyone? So what we have is we have a lot of holes accumulated. Again, it is happening. So this is known as accumulation region. Is there any doubt? Should I repeat? I can do that.
Sir, why
Okay,
don't
sir.
the Fermi levels align?
What are you? Can you repeat?
Sir, why don't the Fermi levels align?
See, we have applied voltage. You should be aware of that. We have done the whole
Oh, okay.
course in which we are using the equilibrium to align the formulas. But in this case, we are having some voltage, so it will not be in equilibrium.
Still
That's
any voltage is applied.
yeah,
Okay.
yeah. So it will be in quasi Fermi level basically. So negative voltage means we will have EFM which is on the higher side, and basically the band will bend upwards because at the interface we have a higher Na. So that means we have a closer Fermi level to the valence band. Does it make sense?
Yes, sir.
Yeah, so that's great. So what happens? I guess this is fine. So when we have this Vg which is less than for a flat band or Vg negative, we have, sorry, what I was writing, yeah, negative. We have the accumulation region, that is I have already written. What is happening in my pen? Yeah. So what I can relate this is with, so we have a certain negative voltage applied. So let's say I can write minus 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 here, and some positive voltage applied here, and in between I have the oxide. So can you relate this? What is this? This is a basic capacitor, right? Does it make sense to everyone?
Yes, sir.
Yeah. So if it makes sense, then if I again try to plot the CV plot, which is negative, so till some point it will be always constant, which is the Cox, which is the oxide capacitance. So what I have tried to explain here is still now here. Is it fine? Now we'll be applying more positive voltage or greater than the flat band so that you will see what will happen. Is it fine till now? See, you need to have the understanding of each and every region. Otherwise, you will not be able to solve a lot of questions further. Is it fine? Shall I move forward? Please confirm. Shall I move ahead?
Yes, sir.
Okay, fine. So now what we'll do is we'll take the further case. What we'll do is we'll make the Vg greater than the flat band voltage. So I hope you are trying to understand this, that before the flat band voltage, the band is bending upwards. At flat band voltage, sorry, what is wrong? So this is Vg less than VFB. At Vg equals to VFB, we have flat bands. And if I apply a voltage greater than the flat band, the band will bend downwards, sorry, upwards. I hope you are able to understand this now. So what I am trying now, I am applying a positive, a voltage which is greater than the flat band voltage. So let's say if I'm applying a greater flat band voltage, so what will happen now? We have a band bending downwards. How I can make this? So this is EFM. Let me try to make it. So this is EC, this is EI, this is EF, this is EV. Or if I give you a very good picture like this, let's say this is VG, which is some positive value. This is SiO2, this is P type substrate. So can anyone tell when I apply a positive voltage, what will happen at the interface?
Negative charge would be
Yeah,
developed because holes would get repelled.
yes. So it will repel the holes, and we know the minority carriers in the P type substrate are Na, right? So they will get attracted. Whatever Na we will have is here. So what it will do is it will create a depletion region at the interface, right? Does it make sense?
Okay,
Yes,
sir.
sir.
Yeah, so if it makes sense, then this particular region we call operation region, we call it as the depletion region, in which what we have band bending downwards, and we have the accumulation of this Na minus at the interface. I hope this makes sense now. So you can see when I'm bending the band downwards, so at the interface, what is happening? This particular thing, which was getting more n plus, this has got intrinsic. At the particular thing, you can see maybe if I try to make this band diagram again, maybe I can make, so this is EI, this is EF, let's say this is EV, EF, EI, EV. So once I make the band downwards, so this particular thing, this EI and EF are getting closer and closer to each other, right? Does it make sense to everyone? Please let
Yes,
me know.
sir.
Yeah. So now what will happen if I apply more positive voltage here? Can anyone tell? If I apply a more positive voltage, what will happen at this particular interface? There, the band will bend more downwards or it will bend upwards.
Downward, sir.
Yeah.
Depletion region would become larger.
Yeah. So what will happen? The band will bend downwards more. So maybe I can make, so this is, let's say, this will be again EC, EI, EV. Oh, sorry. This is what? EF and this is EV. So now what you see, uh, what what we have started is we have started with a P-type substrate. We have the metal, let's say EFM here. And can anyone tell what is the semiconductor at the surface now? Surface means at Si2 interface. What is the nature of semiconductor?
N-type.
Yeah, exactly. So you can see here we have made a semiconductor from P substrate to a N type of semiconductor. So what we have done is we have inverted. So this is particular region is known as the inversion region. So now what? So I'll make two terms here. So the when this EI becomes equals to EF at the interface. So you can see EI become EF at the interface. So semiconductor becomes intrinsic, right? So it went from P to intrinsic to N. Now it has become N type at the surface. So that is why we have the inversion. So does it make sense to everyone?
Yes, sir.
Yeah. So for the depletion region, you can see if I try to make in capacitance terms. So what we have applied some positive voltage. We have some negative accumulation of these Na minus, and then we have a lot of holes. So can I make two different capacitor here? One is due to the oxide capacitance and one is due to this semiconductor. Can I make the capacitance like this, the series combination?
Yes, sir.
Yeah, so if we can make this, so in this particular diagram, so the series combination of two capacitance, I hope you know that C equivalent will be Cox times CSI by Cox plus CSI. So what happens at the depletion region, it basically starts to decrease. So this will happen till a certain voltage when we have got the complete inversion. So does it make sense? The decrease, further depletion. I'll explain the inversion also now. Does it make sense till this particular voltage?
Repeat again, sir.
Okay. So in the previous case, I hope you remember for the accumulation, what was happening is we have the majority holes at the interface and we have the negative voltage applied. So we have a very constant capacitance, which is nothing but Cox. I'm denoting it with Cox. But once we apply a positive voltage, which is this, we have the accumulation of Na, that is the depleted ions, and we have a lot of holes here, like the positive charge. So what I am saying is We have a oxide capacitance which is COX already there, and we have one more capacitance which is this due to the semiconductor which is CSI. So these two capacitance are basically arranged in series, and the series combination of these two, like the equivalent will be lesser than the total COX. Like in resistance we do, if R1 is parallel to R2, like this is, let's say this is 1 ohm, this is 1 ohm. So the R equivalent, I hope you know, this is 1 into 1 upon 1 plus 1, which is half of that. So similarly, the series combination of capacitance is lesser than the original capacitance. Do you understand this?
Understand, sir.
Yeah. So we will have a decrease in the capacitance in the depletion region. And once we have achieved the inversion means we have the semiconductor as the n-type semiconductor. So what is happening here? We have so much positive voltage that we have a n-type semiconductor here. So what happens is it is basically the inverted. So we started from, I hope you remember, from minus to plus. It has inverted to plus to minus. So that is why we call it as first of all the inversion region, and it again starts to increase this particular plot and then again saturates. So it will never go beyond COX. So this is how the CV characteristics has been made for this particular structure. So there are three regions: one is the accumulation, one is the depletion, and one is the inversion. And this is how the CV is getting made. Does it make sense to everyone? So this is the major working.
Sir, could you explain again what is CSI?
CSI, okay, yeah. So CSI is nothing but the capacitance due to silicon, first of all, silicon or the substrate. So what I can write, maybe I have applied a positive bias, sorry again. So I have not applied so much positive bias that it completely gets inverts, but we have some depletion region here, right? Let's say this has a depletion region which has some depletion with D. Does it make sense?
Yes, sir.
Yeah, and we have this oxide which is having, let's say, some oxide thickness TOX. So for this oxide, we have the COX as epsilon ox A by TOX. And for this particular region in which are depleted of carriers, we have this CSI as epsilon ox, whatever the area, sorry, not ox, epsilon SI divided by the depletion region. So these two are connected basically in series. Make sense?
Yes, sir.
Yeah. Okay. So I'll maybe give you some more terms. As I said, so what is happening? So this was a previous case in which, so basically this is EI, this is EI. So I have some terms that I'll give you. This is EF, this is EC, this is EV. So I hope so. This is what we already know. This is what we call as the Fermi potential, the difference phi F. Fermi potential means the change in the Fermi potential is nothing but EI at bulk. Bulk means at, so I'm calling this region as bulk now, and this region as interface. EI at bulk minus EF at bulk. And what we call, there is one more term which is surface potential. Surface potential is
Sir,
nothing.
bulk means, sir,
Yeah, bulk means the this region, this complete bulk semiconductor. So P substrate is the bulk. So everything interesting that is happening, the band bending is happening at the surface. Nothing is happening here. So this region is the bulk, and this region is the interface where there is a change in the electric field. Is it fine?
so fine, sir.
Yeah, yeah, okay. And the surface potential is nothing but, okay, give me a moment. Uh, Surface potential is nothing but EI at bulk minus EI at interface. So you can see here, this is EI at bulk, which is this EF, and let's say this is also equals to, the band bending is equal both sides. So can we say that phi s is equals to phi f plus phi f, which is 2 phi f? Can we say this from this diagram? Any doubts in this? What I have just written?
No, sir.
Yeah. So what happens at the inversion region? This, when this phi f become equals to 2 phi f, we have the inversion region, and at this particular point we have this gate voltage, which is known as the threshold voltage. This VT is called as a threshold voltage. So basically at phi s equals to 2 phi f, we have the gate voltage equals to the threshold voltage, or at, what I can write more is, at Vg equals to Vt, the surface potential is equals to twice of the Fermi potential. Is it fine with everyone? If it is fine, then we can do some numericals now or some more theoretical problems. Shall we move ahead?
Yes, sir.
Yeah, so let's move ahead now. So maybe you all can try to give me the answers now. So in the MOS capacitor, inversion is achieved when the surface potential is equals to the applied gate voltage. When the surface potential is greater than or equals to twice of Fermi potential, the depletion region is fully depleted. The gate voltage is negative for n-type substrate. So can anyone tell what will be the answer to this? So I've got one as B. So the inversion is achieved when the surface potential is greater. Yeah, so that is correct. We have just seen that at Vg equals to Vt, this is happening when this surface potential is greater than equals to 2 phi f. We will always have the inversion. So option B will be correct. Is there any doubt in this? This is, I guess, simple, so we can move ahead. Shall we? Fine. So I'm considering that it is clear. So now we need to find the answer to this. So in the flat band condition of a MOS capacitor, what can happen? So please let me know. I can give you again 2 minutes. You can let me know your answers. I have one answer as A. Please, anyone else also try and let me know the answer. I'll give you 1 more minute. Anyone else have any idea? We already had a good amount of discussion for this particular thing, flat band. Anyone wants to try? Please type in the chat box. Okay, so I have one more answer as A. So let me also try now. So flat band condition is when the energy bands of the semiconductor are flat. So that is correct, yes. So but we should check all the other options. So the surface potential is maximum. So this is wrong. Surface potential is negative. I guess you can now relate. The semiconductor is in strong version. I mean, I guess this was inversion. So this is also wrong. But at strong inversion, we have the band bending. And at strong inversion, phi s is almost equals to 2 phi or greater than equals to. The surface of the semiconductor is depleted. So this is what it means by depletion. So at depletion, we do have a band bending. So all the other options are wrong. So option A will be the correct answer. So this is again a similar question. So quickly let me know what is the answer. So I've got one answer as B. So let's maybe wait for one more answer and then we'll solve it.
Option C, sir.
Okay, so someone has raised a hand. So is there any query? Uh, what did you say? Can you repeat again? Hello? Someone said something.
C,
Yeah.
sir.
What are you saying? What is the answer? Option
C, C, sir.
C. You are saying C.
Yes, sir.
Okay, okay. So let's check now. So I guess some in the chat box. What was the answer? So I've got one answer as A, one as B, and one as C. Okay, so let's check. So what is the significance of flat band? Okay. So it represents the voltage to achieve the strong inversion. So this is wrong. This is nothing but the threshold voltage. It is the voltage at which the surface potential is zero. So yeah, we can have a very quick look. So at flat band, what is happening is there is no band bending. Let's say I'm taking a p-type substrate again. This is EC. So there is no band bending. And what is surface potential? Surface potential is EI at bulk minus EI at interface. So though no band bending means EI is aligned, so it is here also same and it is here also same. So it will be zero. So surface potential is zero. So option B is correct. Then option C is it is the voltage at which the oxide capacitance is minimized. So the capacitance will be minimized when we have the maximum depletion width. That means we are in the depletion region. So at depletion region we have band bending. We do not associate flat band with the band bending. So C is not correct. So does it make sense? Whosoever has said C?
Okay, sir.
Yeah. And it corresponds to the threshold voltage. So this is also wrong. Threshold voltage is when we are in the strong inversion or when the inversion is achieved. So let's move ahead now. Yeah, so this is good now. So we have simplified band diagram for a MOS capacitor. Match the energy band diagrams labeled 1, 2, 3 with the corresponding NMOS and BMOS. I guess I have left one thing. Yeah. In in all the explanation, what I've done is I've used a P-type substrate, right? So for the P-type substrate, what is used is at ultimately inversion, what we got is we have a higher, we have a channel of current due to the electrons. So for the P-type substrate, what we have is we have a N type of MOS cap. So similarly, if I have used the N type of substrate, we have called it a P MOS cap. Does it make sense? This is a very basic thing I left to say. Is it fine with everyone? For P type of substrate, we have the conduction due to the electrons. So that is why we call it as a NMOS. And for the N type substrate, we have the conduction because of the uh, holes. So that is why we call it as a PMOS cap. Does it make sense to everyone?
Yes, sir.
Yeah, yeah. So here because it is written PMOS NMOS, so don't get confused. So let me know quickly what is the answer to this particular problem. Anyone?
The 2 is N MOS, N type MOS.
Sorry, which option you are saying? There is
Uh, 2 is N type PM MOS. PMOS.
so which option are you saying? A, B, C, D, E? Uh, did you say?
D, sir.
Okay, so I've got one answer as B. So let's wait for some more. Anyone else?
B, sir, B.
Yeah, yeah, I've heard B. Anyone else?
Sir, the bias condition is not provided in the options, right?
Yeah, yeah, there is no mice. So it is only asking that which is the kind of MOS cap and the substrate used.
Okay, sir. So in the first line, but they have asked all three. That's why I got a confusion.
In the first, where?
Corresponding substrate type, applied gate
Yeah, yeah.
voltage
So
VG.
there is one more
Bias.
question further. So we'll see that. For now, just try to explain. Tell me this. Any answers? This is very easy. I guess it should not take this much time.
So would you please repeat again uh, the explanation of uh, MOS
NMOS.
regarding MOS regarding
Yeah, yeah,
I
okay.
said
So what I said in very easy language is, if we have a p-type substrate, then we are calling it as NMOS, and if we are having n-type substrate, we are calling it as PMOS. So why? Because for p-type substrate, the conduction is happening because of the what electrons. Because after the application of VT, this particular thing, this at the interface, this p-type of substrate is becoming n-type, right? So whatever is at the interface, that we call as the MOS. So that is why for p-type substrate I'm calling it as NMOS, and for n-type substrate I'll call it a PMOS. That is what I'm saying. So for p substrate it is NMOS, for n substrate it is PMOS. Is it fine?
okay,
Yeah. So I've got, I guess, two answers in the chat box. One is A, one is D, and what did, okay, I've got three answers then, A, B, D. So let's try. This is very simple. Why are you guys? So for the substrate, we can clearly see substrate. So here the substrate, the Fermi level is close to the conduction band. The substrate is n type. Here it is again n type because it is closer to the conduction band. Here it is p type. So p type, p type, p type, p type, n type. Yeah. So option D will be correct. So why are, so option A? So someone said option A. So substrate is not p type for all the three cases. I hope you understand. Is it fine? Are you able to understand? You can clearly see the Fermi level is closer to the conduction band here. It is again closer to the conduction band here, and it is closer to the valence band here. So this is p type, this is n, and this is n. And n means pmos and p means nmos. So that is obviously given in the options. So is it fine? The option D.
yes, sir.
Okay, great. So now let me know the same. Which region it is in? So first is in which region, second and third. Try to give the answer in 2 minutes. If someone gives, I'll also start to explain. Okay, I've got one as E. So I'll wait for one more. Okay, I've got two answers. So let's do it quickly then. So you can see what is happening for the first case. First of all, the first case is again, what is it? This is N substrate. So we have a PMOS. And the interface, what is happening? EI is becoming EF. That is, it is going into the depletion. So depletion is where, yeah. From this only we can say E is correct, but we can see for more options. So at second, what is happening? This is N type, and at the interface it is becoming P type. So we are having a inversion. And again, the depletion is happening for the third. So option E is the correct answer. Shall we move ahead? Any doubts in this?
No, sir.
Next two terms, please repeat again.
What repeat? This again.
Uh, number 2 and 3.
Okay, okay. Number 2 and 3. Okay. So what is happening? You can see at the bulk region we have a N type of substrate because the Fermi level is close to the conduction band, right? And at the interface, this Fermi level is now close to the valence band, or it is below EI basically. So it has become P type. So N type to P type, when it becomes when we reach to the inversion region. This is what I explained for the case above. And same is again here. So we have a N type substrate, and it is becoming intrinsic because EF is becoming equals to the EI. So that is why we have the depletion.
Okay, sir. Thank you, sir.
Yeah.
Clear, sir.
Okay, so now we are moving towards some of the numericals, I guess. So we have a student experiments with a MOS cap by applying different gate bias. The band diagram of the same is shown below. Note that EF equals to EI at the semiconductor interface. It says this. Also, the free carriers are represented in red and blue, where the bound charges are represented in magenta color. Okay, so I will see later for these three things. So the first question is the MOSFET is biased in which region? I hope this is very easy now.
Depression.
Yeah, it is in depletion. So I hope I don't need to have a very large discussion for this. So it will be in depletion because EF is equals to EI at the interface. So option
So
D
then
is
what is deep depletion? Are deep depletion and inversion the same?
yeah, yeah. So deep depletion, I'll let you know. So it is basically related to the applied voltage and also the applied frequency. So in the next lecture, I'll be letting you know about the CV for low and high frequency.
Okay,
So
sir.
in that, I'll be explaining what is deep depletion. So they are not the same, but I'll explain you in the next class. Yeah, so option D will be correct for this as of now. So let's move ahead. So the charge configuration that approximately represent the MOS cap biasing is shown in which figure? So yeah, this is good. Maybe you will get a very good idea if you are able to understand this. So yeah, take your time very quickly and let me know the answer. Yeah, maybe I can make this clear. This is metal, this is oxide, this is semiconductor. Mhm. This is very easy if you are able to
Sir,
understand.
B, sir. Okay.
So I've got different opinions again. So someone is saying A, someone is saying C, and someone is saying B. Okay. So A, B, C, all the three. Okay. So let's go one by one then. So whosoever is saying A. For metal, we cannot have positive charge first of all. Why did someone say A then? Do you understand? We cannot have a positive charge for metal. So A and D will get directly eliminated. Does it make sense?
Yes, sir. Got it.
Yeah, yeah. And for option B and D, we can clearly see that we have a p-type substrate, so we have some abrupt profile. So we will have some, I guess, again, I'll see what we have. Yeah, we have a p-type substrate and it is becoming intrinsic at the interface. So that is fine. But in the bulk region, we have some p-type of substrate. So that will give me option C as the correct answer. Again, is there any difference? Yeah, so someone said C. Yeah. So is it fine with everyone? Option C will be correct.
So why not B?
Yeah, so B will have,
Or
we
metal
have,
cannot have.
yeah,
Okay.
we don't have any, even the trap charges. And even if we have the trap charges, it should be like this, not inside the semiconductor.
Okay. So we cannot have such abrupt variations
No,
on
no,
the semiconductor side.
no, no.
Okay.
Yeah. So let's move ahead. So give the corresponding profile now for the electric field. I hope this is very easy. So let me hold it for you and let me know the answer. Any answer? I hope you remember for a PN junction when we had this. So I've got one as B,
Option A, sir.
I've got one as A. So let me try it. So A cannot be correct because why? Because we will have a negative slope, because I hope you remember for the PN junction we solved for the N side. The corresponding electric field should look like this. So either B will be correct or either C will be correct. A will not be correct, D will not be correct. So now we check. Okay, yeah. So for the oxide field, since we have some negative in this region, so we'll always have the equal oxide. First of all, in the oxide region we don't have any change because it is an insulator basically. So we'll have a constant electric field, and that too will be constant, and that too will be negative because we should have a continuity here. We cannot have some abrupt change in the electric field, because I guess at the interface, I guess you have read this relation. The flux should be continuous, that is epsilon ox E ox should always be equals to epsilon ox, oh sorry, epsilon Si ESI. This is a continuous relation. So whatever the nature of E ox will be same the nature of ESI. So option C will be the more correct answer. Is it making sense? Someone said A and someone said B also. Is it fine? Option C will be correct?
Understood, sir.
Yeah. So let's move ahead then. So now it is asking the field in the oxide region is what at the interface. Okay, so I guess I have already given the answer to this. So this will be solved by the displacement now. So epsilon ox E ox is epsilon Si ESI. So E ox will be nothing but epsilon Si over epsilon ox times ESI. And both of this is given, I guess, in the above. So it is 11.8 and one is 3.9. 11.9 by 3.9. Sorry, 8 by 3.9. I guess this comes around 3 times of ES. So option A will be correct. Is it fine?
Okay, sir.
Yeah. So let's move ahead. So now it is asking the doping concentration in the semiconductor and the electron concentration at the interface are given by. Okay, so it is asking at the interface first of all and at the semiconductor. So here and here, please let me know the doping concentration. Verbally, you can tell the first of all the concept what it should be. Can anyone tell? Anyone?
Sir, could you please show the question again?
Okay, yeah. So okay. So the doping concentration in the semiconductor and the electron concentration at the interface is what? Shall I go to the figure again? Is there a way I can paste this? I'm not sure. I guess maybe I can. Okay, I cannot paste this figure, but
Option D, sir.
okay, I've already got answer. What is the answer? Option? Option, what did you say?
No, sir. Sorry. I don't know.
Okay, fine, fine. So let's calculate. So the ND we need to calculate and the electron concentration at the SiSiO2 interface. So first of all, at the interface, what we know is EF is equals to EI, right? So what does it mean? What will be the electron concentration?
Same as dopant concentration.
Same as the intrinsic concentration, not the dopant. Does it make sense? And is Ni? It will be intrinsic, right? when EF is overlapping EI at the interface, it will be
Yes, sir.
and yeah. So it will be Ni, and at the what this thing is at the semiconductor we know that N is nothing but, sorry, Ni exponential of EF minus EI over KT, and it is nothing but ND. So Ni, first of all, Ni is 10 raised per 10. Sorry, Ni is 10 raised per 10 times exponential of EF minus EI is given as 0.29 over 0.025. So it will come out to be something. So this will be ND, and at interface N will be equals to Ni, which is given as 10 raised per 10 per centimeter cube in the question itself. Does it make sense to everyone?
Yes, sir.
Okay, so let's see what are the options. So electron, so last will be this. So I guess on calculating ND, it will come out to be 1.1 times 10 raised per 50. You can try to calculate at home also. So option B will be the correct answer. Shall we proceed?
Yes, sir.
Okay, great. So now it is asking the surface potential. Surface potential is nothing but EI. Can someone remember the formula? And can someone tell it? What was that? Does anyone remember? Okay, I'll write it then. Surface potential is nothing but EI at bulk and EI at interface. So we can see that here. So EI at bulk is this and EI at interface is this. So basically it will be minus 0.29. I hope you understand. EI at bulk is this particular thing minus this, right? So it will be minus 0.29 volts. Is it fine with everyone?
Yes, sir.
Okay. Oh yeah. So it will be option E. So let's move ahead. The applied gate voltage and the drop across the oxide region is what? So first of all, we need to see the gate voltage if it is applied. So this is the P type of substrate. Sorry, this is N type of substrate, and we are in the depletion. So first of all, we will have a negative gate voltage applied, right? For the N type of, for the P type of substrate or NMOS, we are applying more and more positive voltages to go from what? From accumulation to depletion to inversion. But for the P type, we'll go the opposite way. We'll apply more and more negative voltage. So the gate voltage should be negative, and yeah, the gate voltage should be negative and the drop should also be negative. So basically, what we have the gate voltage as the change in the drop and the surface potential. So what options are there for the negative voltage? We have two options. So let's try with minus 0.78. Surface potential is nothing but 0.29, I guess. What was the potential? So it was minus 0.29. So it will be minus 0.78 plus 0.279. I guess this is matching. Please try to calculate it. Either it will be this or this.
Sir, how we get minus 0.78
So yeah, I just
on the
told you that.
equation?
Yeah. So the gate voltages should be negative for the PMOS to get it into the depletion. So there are two options in which the gate voltage is negative. So I'm trying with both the options. This is more of a uh, guess or answer because we cannot calculate the gate voltage without uh, all the information. So you can try with both the
I
options.
mean,
Yeah, yeah.
want to say that 0.78, how it comes
Uh,
from.
I'm checking for all the negative answers. So I have two options which are negative. So I'm just checking that,
Okay,
and
sir. Okay, sir.
yeah, yeah, and the
Okay, sir.
corresponding, if the corresponding oxide drop match, so I'll check the answer. So I guess this is matching. Option A is fine. It will not match for negative minus 1.07 because it is given a positive drop. So option A is correct. Is it fine with everyone?
Yes, sir. Understand, sir.
Okay. So let's go down. Okay, now the width of the depletion region. So can anyone tell the formula for that? So it will be, I guess you remember 2 epsilon si by q nd times VBI. So here, sorry, it was for a diode, so here it will be surface potential, the difference between the bulk and the interface. Is it fine with everyone? So let's calculate also. 8.85 SI is 11.7, I guess. It's 0.29. NDs, we have calculated the ND in some of the answer. It is 1.110 raised by 15. So this is in centimeter. This is 5, this is 10, 10 is 1 minus 5, 22 by 0.9. Also I have 2 times 8.85 centimeter. So can someone quickly calculate this, or I'll calculate it? Okay, sorry. Yes. It's like QND. I hope I've written everything correct. So I'm getting this as 5.86 raised by minus 5, which is 0.586 10 raised by minus 4 centimeter, and that is basically 0.586 micrometer. So option C will be correct. You can check the calculation once. It might be possible that no. So are you able to understand the whole concept of this MOS capacitor? Is there any doubts that you are still having? Okay, so that is great if you are able to understand this MOS capacitor, because you can see in the weak rate will be more talking about the threshold voltage that we already discussed what is a threshold voltage, but we'll go in deep, and the CV measurements that we have seen how the CV plot looks. So we'll see it for the high frequency and low frequency CV. That in that we'll see what is deep depletion also for the MOS capacitor, and some of the most non-idealities we'll see in the work function. So as you know that I was telling about that there are some trapped charges in the oxide, etc. So that will be considered in the non-idealities. So that will be covered in the next lecture, and some of the leakage current and high K. So we'll see it in the next lecture. So next week I won't be taking any lecture. So we'll meet next Tuesday now for covering the week 8 lecture. So I hope it makes sense, and you all are able to understand how the MOS capacitor works. So with this we can dismiss today's session, and let's meet next Tuesday at the same time. So now I'll be taking the classes from 5 to 7. So thank you everyone for joining, and let's meet next week. Yeah.